Welcome to this explainer. At first glance, a macro shot of a green circuit board dotted with capacitors and microchips might just look like standard, boring hardware. But if you really zoom in, it's like looking at a bustling, microscopic city. We're talking highways of data, towering reservoirs of energy, and intersections where invisible traffic is just perfectly directed. So today, we're going to uncover the invisible forces that govern these tiny cities. We're going to learn exactly how energy flows, divides, and powers the devices that we literally rely on every single second of the day.
Our topic today is the rulebook of the grid, basic electrical engineering. I am absolutely thrilled to guide you through this because, honestly, we're about to decode the ultimate rulebook of electricity. We'll start super small, looking at the microscopic behavior inside just a single wire. And then, we're going to build all the way up to navigating the complex, multi-dimensional matrix of alternating current. So, whether you're looking to synthesize what you already know or you just want a really solid refresher, you are definitely in the right place.
Okay, let's dive into this roadmap for today. First, the foundation, Ohm's law. Second, mapping the grid. Third, the traffic rules, Kirchhoff. Fourth, teaming up, series and parallel. And finally, number 5, entering the AC matrix.
Let's kick things off with Section 1, the foundation, Ohm's law.
So here it is, the absolute golden rule, Ohm's law. Simply put, voltage equals current multiplied by resistance. Good old V equals IR. Think of this as a constant, ongoing three-way negotiation happening inside any conductor. The voltage is the push, right? It's the pressure trying to force the energy through. The current is the actual physical flow of that energy. And the resistance is exactly what it sounds like. It's the material pushing back and slowing the flow down. And the true mathematical beauty here is that if you know any two of these factors, you can instantly find the third.
Let's ground this theory in a real-world example pulled straight from our syllabus. Imagine your normal morning routine. You stumble into the kitchen, you plug in your toaster. Now we know the resistance of the heating element inside that toaster is 12 ohms, and it's plugged into a standard 110-volt outlet. Based on that V equals IR formula we just talked about, how much current is actually being drawn to convert that electrical energy into the heat that toasts your bread? Take just a quick second to ponder the math on that. You just divide the voltage by the resistance.
And boom, there is your answer, 9.167 amps. Honestly, it is incredibly satisfying to see how efficiently Ohm's law solves practical, everyday problems. With just one simple division, we can precisely calculate the flow of electrons required to get that perfect piece of toast.
Moving right along to Section 2, mapping the grid. We're looking at nodes, branches, and loops.
Now, what's really interesting here is when we zoom out from a single wire, we can start to visualize the geography of any network. A branch is just a single element, like a voltage source or maybe a resistor. A node is the exact point of connection where two or more of those branches meet. Think of it as a traffic intersection. And a loop is any continuous, closed path within that circuit. So no matter how wild or impossibly complicated a circuit board looks, the whole shebang is entirely made up of just these 3 geographical features.
And, because the universe absolutely loves order, these features are perfectly bound together by this neat mathematical trick called the network topology theorem. It says the number of branches will always equal the number of loops plus the number of nodes minus 1. So B equals L plus N minus 1. It essentially proves that every single element in a circuit is predictably tied to all the others. You can't just slap a new path onto a circuit without altering the fundamental geometry of the entire system.
Which brings us to Section 3, the traffic rules. We're talking about Kirchhoff's laws.
Okay, so now that we've mapped out our intersections and our loops, we need to understand the laws that govern the traffic flowing through them. Enter Kirchhoff. He gave us 2 totally inescapable rules. The first is Kirchhoff's current law, or KCL. This is the ultimate what goes in must come out balancing act of the electrical world. It states that the total current entering a junction, or a node, must perfectly equal the total current leaving it. Energy doesn't just mysteriously vanish, and it definitely doesn't appear out of thin air at an intersection.
Think about it like this. Say you've got multiple currents, let's call them I1 through I6, all crashing into a single central node. If you add up the values of the currents flowing inward and then subtract the values of the currents flowing outward, the algebraic sum must be absolute 0. It is a perfect, flawless equilibrium at every single point of connection in the grid.
Then we have his second rule, Kirchhoff's voltage law, or KVL. Now, while KCL dealt with current at a node, KVL deals with voltage around a loop.
Based entirely on the conservation of energy, KVL dictates that the algebraic sum of voltage drops in any closed loop must be zero. Think of it as a super strict energetic budget. A closed loop simply cannot spend more voltage than its source actually possesses. By the time the current returns to the start of the loop, every single volt has to be accounted for.
And this brilliantly illustrates that budget in action. If we trace a source voltage pushing current through a series of resistors that form a closed loop, well, as the current travels, that source voltage is meticulously divided up and dropped across each resistor along the way. If you were to walk entirely around one of those closed loops and tally up the voltage you gained from the battery and then the voltage you lost across the resistors, your net change at the end is exactly zero.
All right, moving into section 4, teaming up, series versus parallel circuits.
So, the crucial point here is understanding the structural contrast between these two formations. When components are wired in series, they're connected sequentially, kind of like train cars. Because there is only one single path, they share the exact same current, but the voltage divides up among them. Conversely, when they're wired in parallel, components are connected across the same two nodes, almost like rungs on a ladder. Here, they share the exact same voltage, but it's the current that divides into multiple paths. It's a constant push and pull between shared current versus shared voltage.
Now, you might be wondering, why does this all matter? Let's look at a pretty advanced problem from the syllabus. Imagine you have two 100-watt rheostats. One is 50 ohms and the other is 100 ohms. You need to figure out the maximum voltage they can handle without overheating. Well, the answer changes wildly depending on whether you wire them in series or in parallel. And actually, if you get this wrong, you don't just get a little math error on a piece of paper, you will literally fry your expensive equipment. Knowing your circuit formation is absolutely critical in the real world.
To solve these exact types of problems, engineers use specific resistance rules. In a series circuit, calculating the total equivalent resistance is a breeze. R equivalent simply equals R1 plus R2. The resistance builds sequentially. But in a parallel circuit, the formula flips. 1 over R equivalent equals 1 over R1 plus 1 over R2. Because you're actually providing multiple new paths for the current to flow through, adding resistors in parallel surprisingly reduces the overall resistance of the circuit.
Take a breath because we are hitting section 5, entering the AC matrix, alternating current. We are officially stepping into a multi-dimensional world here. I want to read this quote directly from the source material because it really hits the nail on the head. Scalar numbers were abandoned and complete numbers were used to express the two dimensions of frequency and phase shift. You see, in direct current, everything is just a flat scalar line. But in alternating current, power travels in waves. The simple DC math we just mastered has to radically evolve to handle these rolling, shifting waves of AC power.
To navigate this new matrix, engineers had to literally invent a new mathematical map using complex numbers. And there's a fantastic little quirk here. In standard math, imaginary numbers use the letter I, but in the AC language, electrical engineers use the letter J. Why? Just to avoid mixing it up with our old friend electrical current, which already owns the letter I. By using J, engineers can calculate rectangular, polar, and exponential forms to perfectly track how voltage and current start shifting out of phase with each other over time.
Which leaves us with this final, pretty wild thought. We know from our sources that in a perfectly pure resistance circuit, voltage and current ride the wave in perfect harmony, right? They stay completely in phase. But what happens when you introduce inductors and capacitors into the mix? What kind of chaotic energy ensues when frequency and phase shift take over, dragging the voltage and current completely out of sync? We've successfully made the leap from direct to alternating current today. But let me tell you, the true chaotic depths of the AC matrix are just waiting to be deciphered.